Today I'll start with talking about topological aspects. Little less than that, but still the main ideas. Okay, the main notion is the notion of open set. We will see this, it's very simple, and then we will see how to generalize this. We will not go to the full blast generalization, at least to some level. Okay, the first thing we observe is the following. Suppose if x and y exhaust all these and then just I want to see the probability of the day. In how many atoms one day I will have a pen here on the table which works. Okay, if x and y are any two real numbers, we have the notion of the distance between those 2 points. Okay, suppose x is here and y is here, and the distance is y minus x. And if y is here, x is here, the distance is x minus y. So the distance between x and y is defined as, I'll use this notation, dxy. The absolute value of x minus y. Take the difference, take only the absolute value, and with that we call it the distance between two real numbers. And we observe the following facts. The distance is always greater than or equal to 0 because it is absolute value. And when does it become 0? If it has to become 0, x minus, the absolute value must be 0. The absolute value is 0 only for the number 0. So x minus y must be 0. So x is equal to 1. So it is equal to 0 if and only if x equal to. And common sense, the distance between x and y is the same as the distance between y and x. Because the absolute value of x minus y is the same as the absolute value of y minus x. And most important thing is the following. This follows from the triangular inequality for the absolute values. Absolute x minus y is less than or equal to absolute x minus z plus absolute z minus y, which you have seen before. So this is just called the triangular inequality. Actually, it is these three properties of the absolute value that essentially drives all the calculus of real numbers. Basically, everything is in terms of, comes out of these three properties. These are the foundations of all the analysis. Now, what we do is the following. We first introduce the notion of now maybe before I do that, I could even do something else. Now what therefore we have is, we have a set R we have the notion of a distance between these 2 points R, which has these 3 properties. We can immediately generalize this. Instead of R, we could have taken any set omega, and then we could have defined the notion of a distance between 2 points and omega, which is simply with any 2 points it attaches a number, which is a positive real number, which is symmetric, which satisfies the triangle inequality. Okay. So, it's a generalization. Let omega be any, let's say, non-empty. Let's not worry about trivial examples. Let omega be any non-empty set. Then, by distance function, on omega, let's call it d. We mean a function d mapping omega cross omega, because with two points we associate the distance. So 2 points I have to take, and I get a number. With any 2 points we associate a number such that 1, 2, 3 are satisfied. With R replaced by omega. That is, the distance xy is greater than or equal to 0 for every xy in omega. It is equal to 0 if and only if x equal to y, and the distance between x and y is the same as the distance between y and x, and the distance satisfies this triangle inequality. Now let's look at 1 or 2 examples to start with. Okay. Clearly, R distance defined as O. Okay, then we say omega that D is a metric space. We call that a metric space. So R D is a metric space. Now what we'll do is we'll do several things in RD, and we find that they have an immediate generalization in metric space, because only all you have to do, whatever you have absolute value, wherever you have absolute value, replace it by the distance of that metric space. This is the first example. The second example is the following. Take any set omega. Well, let me take first of all special, very well-known cases. Take omega to be R2. That is our plane, the 2-dimensional plane. So now, suppose I have one point omega, which is omega 1, omega 2, or let me call it x only. X as x1, x2. And y is y1, y2. So these are any 2 elements. We have to define the distance. Define dxy. What is the distance we normally talk about? The distance between 2 points is the square root of the square of the coordinates, difference of the coordinates squared, sum. So it is square root of y2 minus x2 or y1 minus x1 squared, or x1 minus y1 squared, both are same. That you already see the symmetry. I will call this D2 in anticipation of what we are going to do. I will write this as to the power of half instead of writing square. Okay. Now this satisfies all these properties. Certainly it's non-negative. Whenever I say square root, I mean the non-negative square root. When is that 0? If this is 0, if this is 0, sum of the squares is 0 if only each one of them is 0. So y1 minus x1 squared must be 0. So y1 must be equal to x1, y2 must be equal to x2. So the 2 points must be the same. And this is precisely why the name triangle inequality. Okay, if you have point x and a point y and a point z, x to z, z to y is always greater than x to y. The sum of any two sides of a triangle is greater than the third side. It degenerates only if the triangle degenerates into a straight line, then it becomes an equality. Okay, could be done. So these three are obvious. Okay. Then R2, T2 is a matrix space. We shall denote this by from now on. L2, this 2 stands for that I am taking the square, and this 2 stands for there are two components. Now we can generalize this immediately. Instead of R2 I can take Rn, n component vectors. I can define the distance as y1 minus x1 squared, etc., yn minus xn squared. All this will go through. In general, take omega to Rn, define for x equal to x1, x2, xn, y equal to y1, y2, yn, dxy to be summation I equal to 1 to n yi minus xi squared to the power of d2. Then R2, d2, Rm d2 is a metric space. We denote it by, I am going to put some more. Again 2, this superscript 2 stands for always I am taking the square of the distance, square of the component difference, and I will put n here to say that I am talking about n component vectors. Now there is absolutely nothing that goes wrong if I have taken the coefficients to be complex numbers. I have not yet introduced complex numbers, but let's assume that we all know about complex. We all know about complex numbers. So instead of R2 or Rn, I could have taken C2 or Cn in general. Then the only thing is I should put modulus of yi minus xi squared in order to get real numbers, because I want the distance to be real. So in general, Cn comma D is a matrix space where Dn and D2xy now is summation j equal to 1 to n mod xj minus yj squared. And so now we will denote this what by what. So we will write this as L2n C to say that there is complex components. Here I will write R to say that are real numbers. Well, it's a vector space. All that together, it is called this. Okay. This is one immediate generalization. From R to you can go to Rn. More or less that all the ideas that we had on R carried over. We had limit ideas, we can eliminate, we have continuity, we can you can talk about differentiability, you can talk about differentiability, integration. Practically everything you can do in Rn. But be careful about a few things, that's all. Right. Now, consider another example where again take R2 to be equal to omega. Then take a point x which is x1, x2. Take a point y which is y1, y2. Previously we defined the distance as the direct distance from x to y. Now I can say that I am not ever allowed to travel like that. At any time I can move only horizontally or vertically. Then the distance between this and this becomes this distance plus that distance. So we define d1 xy to be equal to mod x1 minus y1, that is this distance, plus mod x2 minus y2. The distance along the x-axis plus the distance along the y-axis. Take the image of that along the x-axis, or the line joining the parallel to the distance parallel to the x-axis plus distance perpendicular to the x-axis. Then certainly it is non-negative. When will it be 0? Again, sum of positive quantities, so each one must be 0. So x1 must be y1, x2 must be y2, so the 2 points must be the same. And it is symmetric. Only thing is you have to verify this. But that follows from the fact that the absolute value follows the triangle inequality. So it's, all these verifications are trivial. Then, therefore, we have R2 D1 is a metric space. However, similar to that, I can make n components. Instead of 2 components, I can make n components and take distances along parallel to each one of the coordinate axes. So, can take Rn instead and define dxy 1 to be summation j equal to 1 to n mod x. Rn d1 is a metric space. We denote this by L1n. That superscript 1 says now we are taking only the first powers or the first mean, and we are taking real components. Similarly, we have Ln1c. Okay. Third is even a little more, okay, I should. More generalization of this. These are called certain type of, these are essentially some types of averages. This is the root mean squared average. In the first one mean average. So we can take in general, instead of the first power or the second power, a pth power. Okay. So in general, define dxy, dpxy to be equal to summation j equal to 1 to n mod xj minus yj to the power of p to the power of 1. Then this is obviously satisfied, again as before. This will also be obviously satisfied, but this will no longer be so obvious. The triangle inequality is no longer so obvious. In the first case, the triangle inequality followed simply. Even in the first case, the n-dimensional situation is not so trivial. So in all these things, the non-trivial thing is the triangle inequality. But therefore, we will have to have certain control over certain standard inequalities. And maybe next class or the class after that, I will just zoom through some of the standard inequalities without proof, but I will indicate why one gets such inequalities. Okay, so to get triangle inequality, we need one must be between P and P. So then we have L, P and R, L, P and C. These are all metric spaces. Okay. So there is now several metric spaces. Now whatever I do in R, any definition which is given in R using only the D idea can be immediately pushed over to a general metric space, in particular to all this. Now We'll give one more. I thought I split the board into the R and the generalization. So now we are doing it. This base is not enough. We'll just look at the idea of it. Is it time? Okay, so now what was the number? Which is numbering is n plus 1. The n is previous 4. Now again look at R2 to start with. R2 to be omega. Define distance between 2 points. Now what did we do here? We looked at the distance parallel to the x-axis and the distance perpendicular to the x-axis. Now what we do is look at the maximum of these two. Either project that fellow along this line and see the distance, or project along this fellow along that line and see the distance. Whichever is maximum you take. So we define it as maximum of mod x1 minus y1 mod x2. We call it as d infinity x2. Okay? Now again it is positive, non-negative. If it is 0, if the maximum is 0, each one of them is 0. So x1 is y1, x2 is y2, the 2 points are the same. And then triangular inequality follows from the triangular inequality, absolute values, easy. So this is a distance, easy to verify. Easy to verify always means I am lazy to verify. Easy to verify that d infinity is the distance. Then we have, we will call it as L infinity to Z R, and in general we can have Ln infinity, where the distance now will be the maximum of the coordinates difference. Maximum over it. So we will have L. Similarly L infinity we can have complex coefficients. So there is a theorem, it's called L infinity because it can show that dn goes to d infinity, p goes to dp goes to d infinity, p goes to infinity. Then there is a theorem which shows such it's a consistency of the notation. Right. A generalization of these things would be, next generalization of these things would be for infinite number of coordinates instead of finite number of coordinates. Just from finite you go to infinite number of coordinates. Now we got into more and more problems, and we have to prove more and more inequalities. Obviously the triangle inequality is going to ask for more and more difficult things. We will come to this infinite things a little later. Now once we look at infinite thing, we should also look at another way of looking at these things. Namely, if you look at Rn or Cn, they are n-component vectors. You can simply think of them as functions on a discrete set 1, 2, 3, n. The f of 1 is the first coordinate, f of 2 is the second coordinate, f of 3 is the third coordinate, f of n is the nth coordinate. So if we look at Rn, first of all, we can interpret this, any x in Rn can be thought of as a function from the set x1 is the first coordinate, x2 is the second coordinate, x of 3 is the third coordinate, x of n is the nth coordinate. So I am storing the function in the form of a vector. So that's all. So x1 simply refers to the value of the function at the point 1. X of 2 says that the value of the function at the point 2. So now what does this distance say? What we are saying is then dp of xy is simply mod x, the value of the function at I, minus the value of the function at I, peak power to the power of 1 over p. The idea would be to generalize this. Instead of the discrete set, try to take a interval or some part of the real line. So let's take some x which is contained in R to start with, and then okay, let me call as S. Then I will look at all functions from S to R. Then what would be the idea of dp between the distance between two functions? I will have to look at the value of the function at each point, look at the peak power and add up all the values. So the adding up will now become the integration over analyzer taking one. This would be the next generalization, but it involves lot of ideas have to be brought in. First of all, we have to worry about when this integral makes sense, what sort of integral are we talking about. See, there are several such things that we have to worry about, and all worrying about all that is about the theory of integration. You have to define the Riemann integral or the Riemann-Stieltje integral or the Lebesgue integral or whatever you want to do. You have to do the right integrals to make these things and then collect all those functions for which this is finite, because there is no guarantee that it will be finite, so only you have to make only those functions for which this is finite and take those fellows and define the distance on them as to be this. That will be a metric space, and that will be the classical Banach spaces or whatever that one deals with. But we will come to this a little later. So what we have is a simple idea of two-component vector can just be thought of as a function on a discrete set consisting of 2 points. N-component vector is a function on a discrete set consisting of n points. Now we can generalize this to an arbitrary set and an arbitrary function, and as long as this integral can be properly understood, the idea of the metric is there. And again, instead of R you could take complex valued, and you could do even more. Any measurable space to all kind of mess we can make. So let's not forget that. Let's not forget. For the time being, various generalizations are possible. Even just the metric situation itself. Okay. So at least we know now a few metric spaces, even though we have not really verified the triangle inequality in all these cases. We will prove certain inequalities which will take care of all the cases one stroke, even the infinite component vector. For everything we will prove one certain inequalities, and then we will be done. Right. So now, I want everybody to switch off the mobile. I should switch off the mobile first. Normally I don't bring the mobile to class. Right. So now we have R, and then we have the distance G mod x minus. What is dp in R? It is the same. There is only one component, p power to the power of 1 over p. So all the p distances reduce to the same distance in the real number case. D infinity, d1, d2, everything is the same. Okay. Now correspondingly we have a general set omega and a metric d. Now we first look at the notion of interior point of the set. I'll even make much notation so that I can just go through the generalization completely. Now, what is a circle? Here is a very interesting question. I keep on making this comment. If you look at our high school books, it is defined as, the circle is defined as the set of all points which are at a fixed distance from a given point. That fixed point is called the center, and that fixed distance is called the radius. Then within another half a page, they will say the area of a circle of radius r is pi r square. Now if you are defining the circle to be that, it has no area. Because It is just it's only a curve, because it is set of all points which are at equidistance from that origin. So it is only that boundary or whatever you call it, and that has no area. A curve like that has no area, it has only length. So what you have tacitly made is you have made a mistake in your definition, or you have not been very careful with your definition. What he means is the set of all points whose distance is less than or equal to r from a given fixed point, and the area of that is equal to pi r squared, where r is that fixed distance. Okay, so there is the moment you define the circle to be the set of all points which are at a fixed distance r from that, then it is no longer area. And that is why we will make our notations here very carefully. So we'll suppose let x naught be any point in R. We will call S x naught R to be the first circle. That is, all those points which are at a fixed distance r from the center x naught. So it is set of all points in R such that the distance from x naught is exactly equal to R. Now in the one dimension, what is that circle? It's just the 2 points. It is just the 2 points x naught minus r and x naught plus r. Then I will denote by BR the set of all points such that dx naught x is less than r. Now what is in one dimension this? I have this point x naught, I have all those points which are at a distance less than r from, so in one dimension R, it will be all those points which are in this interval, x naught minus r to x naught plus r. This is just the set of all points x in R such that x naught minus r is less than x naught less than x naught. And I will use the notation with a bar on it in anticipation of some other notation that I will introduce later, to be just both of them together. Which in this case is simply the closed interval this whole thing. This is just a notation. Now you see that this allows you to generalize. Now let's look at in R2 first of all. Let us look at our L2 to R. So what is let us take a fixed point x naught. The fixed point x naught will have 2 coordinates. Let's call it as x naught 1 and x naught 2, because the point in R2, 2-dimensional plane. Now, what is x naught? We have this point x naught. We are going to look at all those points whose distance from x naught is exactly equal to r. That is that circle. All those points on that circle. So let's call it. This is the set of all x in R2 such that the distance from is exactly. So that is the points on the circle with radius r and center x naught. What will be BR x naught? It will be all these points. It will be the interior, let me call it the interior of the upper circle. You see, there's a this interior is the intuitive idea of interior, because later we'll define a formal definition of interior of the circle. So interior means all those points which are at a distance less than r from x naught. And what is this BR x naught? With a bar on it, it is this full. All this inside and the circle. Okay? The circle and this. What will this be in 3 dimensions? This will become the sphere. This will become the interior of the sphere. This will include the interior as well as the sphere. Now then we have the 4-dimensional sphere, the 4-dimensional walls and 4-dimensional closed walls. Okay, whatever you want to call it. So you can imagine what is going to happen in higher dimensions. These higher dimensional spheres will come. So you take the sphere only, interior only, and both of them together. Okay, that's the first thing that I want to introduce. Okay, incidentally, let us take our L1. What does that mean? Here I am taking 2 component vectors, but I am using the distance, that is the sum of the distance parallel to the x-axis and parallel to the y-axis. Now take the point x naught to be the origin itself. Just for simplicity. 0, 0. What is S or x? What is that? We are here, origin. Somebody says rhombus, somebody says square. Give me 2 more choices. I'll make a multiple choice question and I'll ask you to find the answer. Correct?
All of them, none of them.
Huh?
I mean, square is also a rhombus, but it is
Yeah.
in this diamond.
Okay. Look, let me just draw. You are trying to say, you are saying that let this one,
Yeah.
and this is what? R minus R0, R0. This will be 0 minus R. This will be R0. Okay. 0 R. This is what you are claiming. Right? Everybody accepts?
Yes.
Somebody said square.
I mean, that is also square but tilted.
Yeah. Therefore. Okay. Now I'll put a question mark and leave it here and figure out that. Whether it's right or wrong. So his claim is that this is the that is the what will be the BR? I don't know, assuming that this is correct. I'm not going to verify, I'm not going to say yes or no to your answer. If this were correct, then what will be BR x naught? What is inside? And what will be BR bar? This whole thing. Things are a little more complicated. If you take peek me, the drawing picture is becomes more and more difficult because these will become curves, these boundaries will become quadratic and cubic curves, and that will become, if we are having a cube, it will become LP is going to become. If we have 2, you have a quadratic curve. This is a circle. X1 x squared plus y squared equal to r squared, the standard form of the origin. But if you had a P is equal to 3, then you would have to draw a cubic curve at the boundary, at various boundaries, and that's going to become more and more complicated as we increase it. Okay. So it is not that it is, when I say S is with the intention that in general I will call it a sphere, and this I will call it as a ball. And closure is to say that the ball including the boundary. Right. So now I introduce the notion of an interior point. Now suppose take a set in R, then I don't know what are the elements of R. Suppose I have a point x0 in S. Now this x0 fellow looks to his left and looks to his right. And if by chance all the fellows that he can see on the right up to some distance and all the fellows he can see up to some distance to the left are all in S, that is, are all his friends. Let's say the S elements are friends. So if everybody in his neighborhood is a friend, then that point is called an interior point. So how do I write it? I write this as follows. It means for some epsilon or some R, this whole thing must be inside R, inside S. But the whole thing is called the ball. Okay? So what it says is x0 belonging to S is called an interior point. I'll write it in terms of that notation so that it will immediately get generalized. If there exists some positive radius such that if you take the ball of radius r around x0, it is completely contained. Then it is called an interior point. Now, see, the definition has nothing to do with real numbers. It's only the definition of the ball. And the definition of the ball depends only on the distance. So immediately we have this concept in a metric space. In any metric space, if you have a subset S, a point x0 belonging to S is called an interior point if there is a whole ball around that point which lies interior. So immediate generalization, omega d metric space, x0 belongs to omega is called, S contained in omega, x0 belongs to S called interior point of S if there exists a positive radius such that the ball of radius r about x0 is contained. So this immediate generalization that comes out of these notions. Now we call a set an open set if all the points are interior points. A set is S is called an open set if all the points are interior points. So this definition goes whether it is a metric space or the real line. Okay, a set S. So if I state it in a metric space, it automatically is true for real line because the real line is also metric space. Is called an open set if all its points are interior points. So therefore, if you denote by S0 the set of all interior points of S, then S is open means what? S0 must be equal to all the points must be interior points. Nothing other than interior points are there. Then we say it's a open. Otherwise, S0 will, in general, S0 will be a subset of S. It will be either equal to S or a subset of S. If it is equal to S, then it is called a open set. Okay. In general, S0 is. simplest examples. Let's do with R. Let's say this is obviously an open set. Why? Because you take any point in the interval, you can always put a small interval around that which is completely inside that interval. For example, if you take, let's look at it. Suppose you have a point x0 belongs to S1. Take any point x0. So we have 0, 1. x0 must be in the less than 1. It must be greater than 0 and less than 1. Now what do? You look at this distance and you look at this distance, take the smaller of the two and put 1/4 of that radius interval around it. It will obviously inside. Okay. So let's call let R be equal to minimum of 1 minus x0 and x0. Then look at the R1 x0 where R1 is R by 4. Then clearly it is greater than 0. This is greater than 0. Why? Because x0 is greater than 0. 1 minus x0 is also greater than 0 because x0 is not equal to 1 and it is less than 1. So R by 4 will also be greater than 0 and we are x0 is contained in S1. Therefore S1 is known. Every point, therefore x0 is an interior point. So every point is an interior point and hence S1 is an open set. Now there is nothing special about 0 and 1. I could have put any numbers there. So in that sense, any open interval, that's why it's called an open interval. Any open interval is an open set. Any open interval is an open set. Now incidentally there is a theorem due to Vittal law, later Prof will mention it and even indicate a proof, which says that these are the building blocks of all open sets. These are the building blocks. In other words, every open set can be somehow broken into open intervals. But that's not a big deal. That we will see is very easy to break. But break it up in disjoint open intervals and break it up with at most countably infinite number of disjoint open intervals. So that's the final, the Lindelof theorem says that every open set is a countable union of disjoint open intervals. So the open intervals are in a sense the building blocks of all open sets and hence the entire topological structure of the real line. And that the idea of open interval itself comes through the distance. So the distance idea is the crux of all these. But we can go further and say even that is not necessary. The openness idea is the most important thing and generalize that and eventually get the notion of a general topology. But at least in this line of thinking, at the base of it all is the notion of the distance. On the other hand, if you take this set, what happens to this? Here, if you look at S0, it's only that. But therefore S0 is a proper subset of, what should I call it, what? Did I call it S or S1 or S2? S2 not. So why is this? Point 1 is not an interior point because however small distance I look to the right of 1, I don't find friends. I find my enemies there. So therefore 1 is not an interior point because whatever interval, whatever ball you take around it, it is not completely contained in that set. There is a portion of the set which is outside this set. So therefore, the interior here is a proper subset of S2 and therefore S2 is not an open set. Let us take a finite number of points. And without loss of generality, let's assume that. It's not necessary, but we'll always, whenever we write a finite set in the real line, unless otherwise stated, we'll arrange them in that order. X1 less than x2 less than x3 less than x. Then what happens? Can any point be interior point now? No point can be an interior point because here is x1, next comes x2. What you do is look at the distance between x1 and x2, take 1/3 of that distance and draw an interval. Well, whatever it is, you see a lot of points outside to the left which are not there. And similarly, you draw any interval about this, except this fellow, all others are enemies. This side, except x3 and others, all others are enemies. So therefore, you see that any point is not an interior point. So no point is an interior point. So in this case, the interior is empty. The interior could be empty. It can be empty, or it's a part of S, or it's exactly equal to S. If it is exactly equal to S, we call it an open set. Okay, now one observation which I will not prove, which is easy to see. Whenever I say it's easy to see, that means you have to fill in the gap. This S0 itself incidentally, what can you say about the empty set? Is it an open set? Now we have to interpret it carefully. What we mean by open set is, if there is a fellow in that set, he must have a neighborhood who are all friends. And there are no fellows, why are you worried? So you declare phi to be an open set in that definition, in that idea. If ever there was a point, he must have only friends in his neighborhood. But since that doesn't have any point, I don't have any condition to be satisfied, so phi is treated as an open set. Then, if we take the interior of any set S, S0 is an open set. The interior is always like this. And it is the largest open set contained in it. Largest open set, that is. You scoop out the largest open set from S, that is the interior. If you have scooped up the whole thing, then S itself is an, when S is an open set, you are scooping up the whole thing. So S is the largest open set contained in S, and that's equal to S. Because when S0 is equal to S. Now, some quick properties of open set. As I observed, phi is an open set. Now, if everybody is a friend, that is, if I take the whole set, then every point will be an interior point. Whatever point you take, all neighbors are in the same universe. So, R is an open set. R is an incidentally, in the real line, these are the ones out there. That's not what I want. Suppose now I try to build sets using these open sets as per building block. Okay. What do I mean by build sets? The only way I can build sets is take unions or intersections and then take bigger, more different sets. So if I take finite number of building blocks, namely finite number of open sets, and I put them together and make a bigger mass, will that be an open set? The answer turns out to be yes. If I put countably infinite number of such building blocks and make a mass, I will still get an open set. If I put any number of open sets and put them together, the big mass is still open set. So what we want to say is, by unioning open sets, you are not going to get anything new. Okay? Your thesis will be rejected. Same thing you are saying again, you haven't gotten anything new. So the union of any number of open sets is an open set. So if A alpha, S alpha, alpha belonging to some index at I, in any collection, finite, countably infinite, or uncountably. Any collection, maybe a finite collection or countably infinite collection or an uncountably infinite collection of open sets, then union of all these fellows is also an open set. Now I will quickly indicate the proof of this. Now you will see that all these state proofs are valid in the general metric. In the general metric space, what will happen? Phi is an open set, omega will be an open set, and if you take any collection of open sets, the union will also be an open set.
Sir, one thing, is this notion of openness relative to some basic metric space that you are taking? For example, if you take a set of rational numbers, open rational numbers, let us say, they need not be closed in R, but they might be closed in...
I am not talking about closed yet.
Okay, open in R.
Yeah.
But then, like...
Yeah. So therefore, what? See, remember, what did I want to form metric space? One, a base set omega, and the other is the distance concept.
Yeah, that...
If you change any one of them, you are getting a different universe. It's a package deal. I am going to call this pair as a metric space. In this pair, this is an open set.
Okay.
If you change any of things, so the
Okay.
definition involves everything,
Okay.
isn't it? I am taking a subset of omega,
Okay.
and if I am taking all x in omega such that d is less than. So the omega is involved, subsets of omega are involved, the distance concept is involved. So it is a clear-cut thing. You know exactly which universe you are talking about, and you must know clearly which distance you are talking about. There is no question of confusing all these things. So base set is important and the distance is important, and all other notions are within that universe. Like when you are talking about a line or a plane, you must be very, or a point and a line, you must be clear about which geometry you are talking about. What are your notions of point? What are your notions of line? Which is the collection of points? Which is the collection of line? Depending on what you are talking about, you may get Euclidean geometry, you may get Riemannian geometry, you may get Lobachevskian geometry, all kinds of geometries you get. It's exactly like that. Tell me what are your points, omegas first. Tell me what do you mean by distance. From now on, don't tell me anything, I will tell you. This is what is an open set, this is what is. That's it. Okay. Alright, so now let's look at this. I will first look at 2 sets, then see 3 sets, 4 sets, then see what's the problem. The reason I am doing it is, the next question will try to do similar thing and see where things may fail. Okay. Suppose S1 and S2 are 2 open sets. Okay. And I want to look at the union. I am claiming S is an open set. I want to claim. I am investigating, first of all, whether the union will be an open set. What is it that I have to do for that? I have to take any element in S and show there is a full ball around it which lies completely in that set S. So take any element take any x naught in S. We want to see if there exists a positive radius such that PR x naught is contained in S. This is what we want to see. If the answer is yes to this, then we know it is an open set. Okay. So all that we know is x is given in S. So x naught is given in S, and the only thing I know about S is that it is the union of S1 and S2, and therefore x naught must belong to one of these fellows. So this says x naught belongs to S1 or S2. Now, what does this mean? Now, S1 is an open set. If S1 is an open set, there will be a ball about x naught which lies completely in S1. So, there exists an R greater than 0 such that BR x naught is contained in S1. That is because S1 is an open set. Because S1 open. But then S1 itself is a part of S. So this says there exists an R greater than 0 such that BR x naught is contained as equal to S because S1 is contained in S. And we are done. We have got a ball around x naught which lies completely in S. Okay. What will happen in this case? All the S1s will become S2s, but S2 is also a part of S, so the same argument will carry through and we will get that there exists an argument here x naught. So in any case, you can always find a ball around x naught which belongs to S. Now, is there anything restriction in continuing this argument for 3 sets? 4 sets, n sets, any number of sets, same argument continues. Okay? Similar arguments for similar arguments. So what will happen? In the general case, if I have this, it will say x naught belongs to S alpha for some alpha, but S alpha is open, therefore there will be a ball which will contain in S alpha, but S alpha is a part of S, therefore I will have a ball contained in S. So that's the simple argument, so you get everything. So similar argument for general connection. So the union of any number of open sets is always an open set. Now, therefore, from the point of view of building, we are not going to achieve anything by going on taking unions of open sets. So we try intersection of open sets. It doesn't work. Let us look at intersection of open sets. What can we say about intersection of open sets? Let's first look at this and then say it. Now let's again start with 2 of them. Okay. Suppose I had S1, S2 open sets. See, I am not writing now in R. I can take any general metric space, same arguments go through. So I will say open sets and leave blank here. You can take any metric space and in that metric space this is also good. Suppose S1 and S2 are open sets and S is S1 intersection S2. S is S1 intersection S2. Now, is S an open set? For that, we have to see star again. So, the star. Same question. Whenever you want to verify whether something is an open set, we want to verify that. Whether there is a ball around that point, take any arbitrary point, and find a ball around that point. Let's follow the same argument as before. Now see what happens. x naught belongs to S. Previously we said therefore x naught belongs to the union. Now we will say x naught belongs to the intersection. Now that says x naught belongs to S1 and x naught belongs to S2. It is AND now. Now previously it was OR. Now it is AND. Now this says S1 is an open set, therefore there will be a ball around x0 which lies in S1. So there exists an R1 greater than 0 such that BR1 x0 lies in S1. In the previous step, in the previous union case, we could immediately conclude therefore it is also in S because S1 was part of S. Now S1 is no longer a part of S. S1 is bigger than S perhaps. So we cannot jump from the conclusion, we cannot jump to this step. This is now not allowed. So we are in trouble. In order to show something is in S, you have to not only show it is in S1, you should also show that it is in S2. Or it's not only in S2, it's not enough to show it's only in S2, but you have to show it in S1 also. You have to show it in both. So now, this says, because S2 is open, there exists maybe another ball, because it's not necessarily the same ball as such that BR2 x0. What have we done? We have found two balls, but we wanted to find one ball which lies in both of them. What will you do? Take the smaller of the two, isn't it? Because the center is the same. Since the center is the same, one ball is there, another ball is there, one of them must have bigger radius. So therefore take R minimum of, so implies BR x0 is contained in S1 and S2 if R is minimum of R2. Is that clear? And we are done. Because it will belong to S1 and S2, so therefore BR x0 is contained in S2 intersection S2 which is equal to S. Therefore S1 intersection S2 is. Okay, so the intersection of two open sets is not going to give you anything new. Again, it's going to give an open set. Suppose I put 3, what will happen? Again, I will take minimum of R1, R2, R3. Still, instead of just the minimum of R1 and R2, I will have to take minimum of R1 and R2 and R3, and it will still work. Notice, R is greater than 0. Why? Because R1 is greater than 0, R2 is greater than 0, the minimum is one of them, so it will be greater than 0. Similarly, if you take 3 sets, R1 will be greater than 0, R2 will be greater than 0, R3 will be greater than 0, the minimum is one of them, therefore it will be greater than 0. So finite number, no problem. So the finite intersection of open sets is an open set. So similarly, I'll write this. Similarly, if S1, S2, Sn are open sets and S is equal to intersection of Sj, J equal to 1 to n, then x0 belongs to S implies x0 belongs to Sj for every j, which implies, I'll just write the steps, which implies there exists an Rj greater than 0 such that Vrj x0 belongs to Sj for each j, which implies Vr x0 belongs to Sj for every j, R equal to minimum of R1, R2, which implies Vr x0 belongs to S intersection of Sj, which is equal to S, which implies Okay, so that's a quick summary of whatever I said. Now, this R is still greater than 0. Suppose I take a sequence of open sets, S1, S2, S3, S4, etc., etc. Now what will happen is I will get an R1, R2, R3, R4, etc., etc. The minimum need not be 0 anymore. Now we come to the greatest lower bound, the infinite. One of them, the first one may have a ball of radius 1, which is lying inside. The second one may have a ball of radius half, which is lying inside. The third one may have a ball of radius 1/3, then 1/4, then 1/5, 1/6. Which one are you going to take? Whatever ball you take, but later fellow goes inside that. So you cannot have a single ball which is contained in all of them. So the minimum could turn out to be 0. And that so, but we want the radius to be positive. So therefore, this argument fails because the minimum could be 0. So it's not necessary. So if we have infinite number of sets, then R could have become 0. So we cannot conclude that intersection of infinite number of open sets of infinite number of open sets. Take for example the point 0. Take -1 to 1 to that interval to be a set. Okay? Each one of them is an open set. Okay, they are open intervals. But what is the intersection? Just the single point 0. The thing that is common to all of them is a single point 0. And we observe that if you have a finite set, it cannot be an open set. So 0 is not an open set. So the intersection of an infinite number of open sets need not be an open set. So the only thing decisively we can say is the intersection of a finite number of open sets is open. So the only thing we can decisively say is the intersection of a finite number of open sets. In the case of the intersection of infinite number of open sets, it may be open, it may not be open. I am not sure. I cannot say this. Anything could happen. It could turn out to be an open set. It could turn out to be not an open set. We cannot say anything decisively. But what we can say decisively about infinite sets is the union has to be always an open set. Therefore, in the building process of Bayer, the new sets, starting from open sets, the new type of sets that you can think of building comes only when you take intersection of infinite number of open sets. You are maybe getting something new. You may not get open, you can also get something new. And that's how Bayer started building his sets called G delta sets, and then later he came about G delta sigma, F sigma delta, all kinds of Bayer class of sets. Actually they are called Borel sets. Bayer had it in a different context for connection of continuous function. Rather call them Borel sets. These were all, see the Bayer and Borel and others played around with these cells quite a bit. I'll be mentioning their names very often. Okay. So now we have these are actually, after a long experience, you realize that these properties are the ones that are crucially used. It is not even what the distance is, it is not even what the space and all. The idea is always these properties in the open sets that basically control many of calculus. So in fact, people generalize it. This itself is the notion of topological spaces. But I will give that. So but basically what is there for, what would people call as a topological space? You start as a omega, any set, don't even bother about the distance. take some collection of sets and call them, designate them as open sets, as long as they satisfy these properties. So the empty set is also an open set, the whole omega is also an open set, and the union of open sets is open, and the intersection of open sets is open. So in other words, any collection of subsets of omega is called a topology if the whole set belongs to it, empty set belongs to it, it is closed under arbitrary unions, and it is closed under finite intersection. So that is the general definition of a topological set. Omega, non-empty set. Tau, a collection of subsets of omega such that 1, omega belongs to tau, 2, phi belongs to tau, 3, A alpha belongs to tau, implies union A alpha belongs to tau for any such union, and 4, A1, A2, AN belong to tau, implies intersection J equals 1 here, AJ equals 2. Then tau is called a topology. Omega and omega tau is called topological space. Now if you look at R2, we have the distance, the Euclidean distance, D2 distance. That gives rise to a notion of open sets. Take all those open sets and put them as a tau, and that's a topological space. But you also have another distance called the D1 distance. That will give you another collection of open sets, and that will make it another topological space, and so on and so forth. So it is look like I can put a number of distances, each one will give me a topological space. But we will see that essentially all of them give us the same topological space. That's at a later stage. But right now we will not bother about it. Essentially all of them give the same. But in infinite dimensional spaces, there is, that's what, this is what generally people refer to as the finite dimensional fiasco. Apparently we are making a lot of noise about different things, but all the different things are the same things. Okay. But in infinite dimensional, they are indeed different. So therefore, for example, R with tau as the open sets as defined above, then R tau is a topological space. In general, omega D is a topological. Any metric space is a topological space. And of course, there is a new question whether big question and theorems in topology that suppose I start with an arbitrary collection of sets which satisfy these properties, I will call them open sets. Is there some distance with respect to which these open sets will be precisely generated? This is called whether the topology is metrizable, and there are sufficient conditions, necessary conditions, there are theorems which says under what condition a topology will come from a distance, under what conditions the topology may not come from a distance. These are all questions of very fundamental nature in topology. Okay. Now for everything there is a dual. For the open sets there is a dual. That is what are known as closed sets. It's a sense. Anything, it's not like this. Anything that is not open is closed, is incorrect. Is the office open? No, it's closed. But in topology that's false. No, it is not open does not mean it is closed. Okay. So whereas in an office we go and say, is it open? No, it's not open. That means it is closed. But it is not true in topology. Okay. So the closedness is a dual property to openness. You say a set is closed if its complement is open. We say a set is closed if its complement is open. So it could happen that the complement is neither open nor closed. The set may be neither open nor closed. There are open sets, there are closed sets, there are sets which are neither of these two. They may be neither open nor closed. Half open, you keep the door half open. Okay. So it's neither closed nor open. Because you see that when you go to see some professor, the door is half closed. You hesitate for a moment at the door. Shall I knock? Shall I go? When the door is closed, you happily go and knock. Or when the door is open, you see I'm walking. But it is when you are this half business, you are a little bit hesitant. Okay? That's exactly what's happening. That's psychology. Right. So on the next class, I will start with the notion of closed sets, and which come from open sets. So one way is to start with the notion of open sets, and then define the notion of closed sets through the open sets being those which are complements of it. But there is another way. You can start with closed sets, within the definition of closed sets and the notion of closed sets, and then define the open sets as the complements of closed sets. Either way you can approach. So okay, we'll see either way what one does. Now these notions are the most, I am going to not only talk about open sets and closed sets. These are the fundamental types of subset that one would keep coming across to get some results in analysis. I will also look at several other types of sets. For example, I may talk about dense sets. I may talk about nowhere dense sets, everywhere dense sets, somewhere dense sets, and so on and so forth. Okay. There are a number of perfect sets. Okay, so there are a number of types of sets that I will talk about, and all these are very important. Every type has certain characteristic of its own, gives certain results, and which are of importance. Okay. Compact sets, non-compact sets. These are all very important. Connected sets and not connected sets. So there are lots of interesting types of sets. Each one of them has its role to play in generating certain properties. Okay. So after I discuss all these types of sets, I will get into very quickly about sequences of real numbers, sequences and series of real numbers. Then I will get into functions, continuous functions, and properties of continuous functions. Then probably semi-continuous functions and the notion of how maximum, minimum can be talked about for semi-continuous functions, and how the compact sets, other things come into play in these decisions. Okay, that will be the rough note for the next few days.